guys, welcome back, and we are still in our series of understanding what are registers, how they operate inside, and how they are connected to different circuits in a system. So last time I demonstrated a 2-bit serial input serial output register, and I showed you the connection using the logic gates. Yeah, we used the logic gates to make the serial input serial output. I showed you the connection of the clock, how the clock is connected inside of a shift register, which is going to be a serial input serial output register. So today we are going to do just the same serial input serial output register, only that this time around we have 4 flip-flops. So we are going to shift data into 4 bits. It's going to be a 4-bit serial input serial output register. And these are the connections. You can see the clock is inverted to the second and the fourth flip-flop, and the clock is not inverted into the first flip-flop and the third flip-flop. So that was the sense. And last time I explained that for a shift register to operate the way it does, it has to process data either in the rising or the falling edge of the clock signal. So either in the rising or the falling edge, there has to be a flip-flop which is enabled for the data to shift from one point to another. Like for example, if the clock is taken, it has to be high in the first flip-flop, then this next flip-flop it has to be low. That's why there is an inverter. Then in the third clock, it has to be high again. Then in the fourth clock, it has to be low, falling edge. That's why there is an inverter. So that's basically how the clock signal is connected. And our circuit is a serial input serial output, meaning that it has only one single input and it should have one single output. But for my case, you can see that I've taken output into the different sections, into different outputs of the flip-flop. This because I want to demonstrate and I want to show you how data shifts from one flip-flop to the other. But in the real sense, a serial input serial output should have only one input and one output. In our circuit, you can just take your output right here, rather than taking output from all this, because it's just going to shift until this point. So you can take your output only into this section, leaving all the others. But because I want to demonstrate, I want to show you how data shifts from one flip-flop to another, I'm going to connect my output lines into those different flip-flops. Yes. So for the 4-bit serial input serial output, I'm going to demonstrate that using an IC. So this is an integrated circuit called 74LS195A. It's let's say it's a general purpose shift register, because it can do serial input serial output, parallel input parallel output, parallel input serial output, serial input serial. So you can do basically all those configurations in one single IC. So it doesn't necessarily looks like this inside, because it has a lot of circuitry. You can look even it has a JK flip-flop in pin number 2 and pin number 3. So it basically has some other circuitry inside to help this function the way it does. So for in the IC, just as we have seen, pin number 2, pin number 3, JK flip-flop, the clock is pin number 10, and the input lines for the parallel, if you want to use parallel, are pin number 4 to 7. If you want to use parallel, you're going to use pin number 4 to pin number 7. Those are input of the parallel. If you want to use serial, like in our case, which we have connected in serial manner, we use J and K only. J and K as the input of our serial. The serial input connection, J and K only. So this will leave them open. The output is taken from pin number 12 to pin number 15. That's where you get the output. So if you want a single serial output, you can just take it from pin number 15, because it's just going to shift, and you're going to be able to connect like that. Yes. So as we have said, okay, we also have pin number 1, which is inverted. These are clear. Clear input, meaning that it clears everything. Which the flip-flop had stored. So you can see it has an inverted section. So meaning we have to keep this high. We have to keep number 1 high in order for it to be low. If you keep it high, it's going to be low, and when it's low, meaning that you can operate inside, you can operate what you want. So we keep this high when we want to use the IC, and we keep it low if we don't want to use, or we want to disable the IC, we keep it low. Yeah. Pin number 9, we have a parallel enable. In some data sheets they say it's shield, some sort of shield enable. I don't know really well, but for in this for the one I was using, it was a parallel enable. It was called the parallel enable number 9, and it's inverted, meaning that when we want to use this IC as a parallel input, parallel output, we have to keep this low. If we keep it low, then it's going to be high. But since we are using it for like in our case, we want to use it, you use the IC as a serial input, serial output, we have to keep this high in order to disable the parallel section. So when this is low, you can't use the serial, but when it's high, you can use the serial connection. So that's basically how the IC looks like. And pin number, the pins which are not here, pin number 16 is a VCC, and for our IC, the maximum rating is just around 5 volt, maximum of 5 point something like 5.2, 5.3 there. Yeah, that's the maximum. And the minimum is 4.5. Yeah, 4.5 there, 4.8. You can just check there in the data sheet of this IC before you start connecting it. So that's basically all about the 74LS195, and that's what I have in the breadboard. So let's go straight ahead and look at our connection. So this is the 74LS195. You can see it's a big IC. Yes, and the connections are right there. So here in the first place we have NE555 connected in oscillator mode. This is the clock pulse of the whole circuit, clock pulse of the whole circuit. So we are controlling the clock using the NE555, and I did a video on how to connect NE555 into oscillator mode. For those new viewers, I'll just put the link below in the description for you to just go and check how you can connect an NE555 in 3 modes. We have oscillator, we have monostable, we have bistable. So you can see here we have a capacitor that we are using to control the frequency at which our oscillations are going to be, and I'm using a 220 microfarad. It's quite slow, but just as we have said in the previous videos, I'm using this one quite slow for you to understand. I want to show you basically what happens individually, or slow for you to quite get the concept of what happens inside the circuit. So we have the LED. This is an LED to show you the clock signal. Then we have a dip switch right here. I'm using 3 of those switches. Switch number 1 is the J. You can see here pin number 2, J. So this one goes all straight to J. Then pin number 2 is K. Pin number 2 is K. And as we have said, pin number 1, we keep it low. So this is the pin number 1. So we keep it low. We keep it high. We keep it high. So at all times, you can see it's already on. At all times, we want to keep this high when we want to use the circuit. If it's low, you can't use the circuit because you are clearing everything that is in the flip-flop. The clear. This is how the clear is connected into those flip-flop. All those flip-flop have this connection, below here. So this is the clear. It's connected into all these individual flip-flops. So once you turn it on, you are going to clear everything. once you turn it off, you're going to clear everything because it's inverted. If it's off, it's going to be 1 and it's going to clear everything that you have stored into your flip-flop. Once it's low, it's going to be high, so it's going to clear. Once it's high, then once you've put high, then it's going to be low, so it's going to basically halt the process of clearing the flip-flops. So you can do whatever you want with your flip-flops. Yes, so we continue. This is the IC. You can see here pin number 7, if you have said, is ground. Pin number 16 is VCC right there, and the output lines are taken all the way from pin number 12 to pin number 15 right there. Pin number, I think pin number 10 is the clock. Yeah, pin number 10 is the clock. This one comes from the NE555, and this pin number 9, as we have said, pin number 9 is a parallel enabled. So since we are not connecting this IC into parallel mode, we have to keep this high. You can see I've connected it directly to the power supply, so it's high, meaning that it's going to be low inside. So we have disabled this parallel connection. So basically this is disabled, so for us to use this serial input serial output connection. And the LEDs are right there. We are using blue LEDs and the resistors, 1K resistors, to protect the LED from the current. So that's the connection, and let me power the circuit and we can start the demonstration. So power is on. You can see the LED is starting to flash. So that's the clock pulse with which the NE555 is producing the signals. So that's how the signals are being created slowly by slowly. So if I want to input data, if I want to put data in my circuit right here, I have to manipulate J and K inputs for me to get what I want. In my experience, I've seen that maybe the input K is quite inverted. It's inverted, and I think it conducts into the falling edge of the clock. I think so. It conducts into the falling edge, or it's connected into the next clock pulse of the J. So let me just demonstrate for you to see. So if I want to put data, I put 1. So it's on, and that one shifts from one flip-flop to another. Then it continues on because I've not put it off. Let me just put 1 for you to understand well. Let me just turn it off like that. Let me just put 1, then I'll turn it off for us to see. Okay, let's wait for the clock pulse right there. Now I've turned it off. So that one goes from flip-flop to flip-flop until it goes out of the circuit like that. So if you can remember, as when we said that there's a serious drawback of the serial input serial output is that you have to wait for those 4 clock signals for you to start receiving your data. You can see after those 4 clock pulses is when you're going to start receiving your data. So that's a serious drawback of the serial input serial output connection. So we do that again, put 1, then I'll turn it off. So that one goes from flip-flop to flip-flop, and you have to wait until those 4 clock pulses until you start receiving your information. So it's a 4-bit. So let's say I want a code like 1010. Want this into our flip-flop. So I basically start with a 0. So a 0 just means that the circuit is not on. Let me just turn it like this for this, or I can just write the codes right here above so that you can see 1010. So we want a code like this into our circuit. So basically we have started. Now the first one, we always start with the LSB. LSB means the least significant bit. Then we go all the way to the most significant bit. This last one is the most significant bit. So we start with the least significant to the most significant. So we start off with a 0, then a 1, like that, then a 0, then a 1, and our circuit is off like that, So let's do that again. We start with a 0, then a 1, then a 0, then we turn off this one. Okay, I've turned it off a little bit early. Let's do that again. 1, 0, then 1, then we turn it off. So 1 0 1 0. So in a brief moment, we had our chord here before it continued on, because it's not going to stop until because you are just receiving the data. Let's say this is the receiving point. It's not going to stop. It's going to continue feeding the receiver the information that you have put there. So let's do that again. So it's a 0. Start the 0, then a 1, then a 0, then a 1, then we have it 1 0 1 0. Yeah, so in the brief moment you have seen that we had our chord 1 0 1 0 before it started moving and clearing from the flip-flops. Let's do another configuration. Let's say we want to store a data like 1 1 0 1. Okay, 1 1 0 1. Let's do this. So we start off with the least significant. So we start off with the J. So we went for the clock pulse. J, 0, 1, then K. I've missed it. Okay. Let's do that again. We go with J, 0, then 1, then 1. So 1 1 0 1. We have our chord like that. Before I've forgotten to turn this off. I've forgotten to turn it off. Okay, let's do that. Let's do that again. We wait for the clock signal. We put 1. What's up? What happened? Okay. Oh, I've turned off the enable. Okay. So let's do that again. Wait for the clock signal, then we're going to start. Okay, 1, then 0, then 1, then K, and then turn off. I've turned off the enable again. Come on. Oh, this is quite hard. Okay, let's do that again. So we wait for the clock signal, we turn it on. 1 0, then 1, then 1, like that. 1 1 0 1. So 1 1 0 1. So that's the code that we wanted. Let's do that again. That's quite fun. Let's do that again. 1 1, then 0, then 1, then 1, and then we turn it off. So 1 1 0 1. So in a brief moment, you have seen that we had our code 1 1 0 1 in all the flip-flops, and the data is continuing to move until it goes out of the flip-flop, because it's shifting. That's the sense. It's just shifting. Let's do our last configuration, and I demonstrate another real cool stuff that I wanted to show you. So this is the last configuration. Let's do 1 0 1 1 1 0 1 1. So this, we have 1. We're going to start with 1, then we go to 1, then we go to 0, then we go to 1. So let's try that. Wait for the clock signal. 1, then 1, then oh, I've turned off the enable. I'm not okay. Let's do that again. 1, 1, then 0, then 1. So in a brief moment, 1 0 1 1. You can see in a brief moment we had our code 1011. So that's basically how the flip-flop function. Only that you're not in a system like, let's say in a computer, let me turn it off. In a system like, let's say in a computer, it always has you're not always the one to control this, because let's say when you're tapping the number 0, and it goes into a 4-bit register. So 0 is going to be 0 0 0 0, or let's say for a number like 4 or 5, let's say 5. 5 is going to enter an encoder. Then the encoder is going to change that circuit or that information that you have typed, number 5, into 0 1 0 1. Then that 0 1 0 1 is going to enter these points, the J and K, and it's going to be manipulated, and it's shown in the register, or it's stored in the register for a brief more into the future for further purposes. If you want to do calculations, let's say 5 plus 5, it's going to store them into the registers. Then when we want to do them, then it does like that. So if I want to demonstrate demonstrate a simulation, let's say how a computer does inside, on how it processes the data and it shifts from one point to another. To do that, I connected two NE555s together. These are two NE555s. They are not connected together. They have different outputs because these capacitors are of different ratings. So the clock signal, they are connected in oscillator mode. So the clock signals are varying. So I want to connect these two lines into the J and K. So for you to see how maybe a computer works inside and how it operates inside. So I'm just going to shift this power supply to the top breadboard. Once I've shifted, let me just turn it off for me to connect this first. Just connect this, and yes, let me connect it. Just use another pin, yeah. I don't know if it's like that. Then this is the power supply, so I connect the power supply like that. Then the ground, this is the ground, so let's connect the ground. Wow, like that. Yeah, okay, let me just, yeah, like that. So we are going to just remove these two. We are not using them for now. So they have different speeds because they are different capacitors. They have different frequency. Let's call that frequency. So when I turn it off, when I turn it on, the different clock signals, you're just going to use them as the binary digits which are entering the J and K inputs of our IC right there. So according to how they are varying, that is going to be shown into our LEDs right here, and it's going to be it's going to display what really happens, or what is really happening into those two different inputs or outputs of those NE555s. So let me turn it on. Yes, let's see. Goes. Another one comes in. So according to how different they are, you can see. So I want to demonstrate, show you, like in a system like a computer, inside it processes data non-stop. So data really just comes and just goes from different sections, from here, from the adders, from subtractors, from sensors, from anything. Just process the data at random. Just process the data randomly. So I'm just going to remove this and I'm going to enter it again. I want to vary the connection here. Let me see. Let's see. 11111, and it halts. Let's remove that. It's varying again. Goes, and another one comes in. Goes on. This is number 5 in binary. 0101, 1010, 0101, and it just keeps shifting on. 1010, 0101. So so in a computer simulation, if you are doing some typing and you are doing something, this is what really happens inside. The computer reads what you are doing in terms of binary and saves it into different registers into the computer for you or to get what you really want, or the instruction that you have given the computer or any other system. Like a simple calculator is going to do some quite of binary connections like this one, with the adders, the subtractors, and the multiplexers, and the ALU, and different circuits right out there. So I really hope you have enjoyed our episode today, and we are going to move on. So next time we are going to see parallel input, parallel output connection. And I hope you are really going to understand. So thank you very much, guys, for watching. Please subscribe to Tronic Zenergy, where we do fun stuff all day, all the time.
So keep me in your sight.